All right, here are graphical representations of a function. So all you have to do is just observe and find out whether the open intervals on which the function is increasing and decreasing. And then it says identify the functions local and absolute, if any, saying where they occur. Okay, so let's answer letter A. Where is it increasing? And make sure you read the problem. It says find the open intervals. So let's see, where is it increasing? On the interval starting from -2 up to 0, and then at the same time from 2 to 4. You see that the graph is increasing and it's increasing. Now remember, you have to always start from left going to the right. So you find yourself, what you can do is just let this ball roll down. That's where it's decreasing. Then roll up, that's increasing. Roll down, it's decreasing. Go up, it's increasing. Okay, so the function is increasing on the interval. See, from -2 to 0, you see how it rolls up. So from -2 to 0, and then from 2 to 4, you see how the curve goes up. So from 2 to 4. Remember, these are the intervals on the real line that you have to identify the interval where it's happening, where the increase or decrease is happening. And then decreasing on the interval from where? From -4 to -2, and where else? From 0 to 2. 0 to 2, you see, if you run from 0 to 2, the ball is rolling down. Okay, and then letter B says identify local. So let's see, where are the local max? That's a local max, local max, and local max. So we say x equal to, when x equal to, well, we might as well locate the point since it's a graph. Okay, so local max would be at the points -4, 2. Now remember, these are not intervals, these are points. And then you have 0, 1, right? When x equal to 0, y is 1. And then when x equal to 4, y is -1. So when x equal to 4, y is equal to -1. Okay, and then local min occurring where? You've got a local min right here and right here. So you have two local mins. So it's at -2, 0, and also to -3, right? When x equal to 2, y is equal to -3. So when x equal to 2, y is equal to -3. And then out of the local, pick out the absolute. So I'll just put a capital A to mean it's the absolute. So you take all those values and that's your absolute, because that's the largest y value. So absolute max. And then here between these two, there's your absolute min. Okay, you do the same thing here. Find the open intervals on which the function is increasing. So let's go ahead and take those intervals. Okay, on the intervals, I'll better write it down, that way you won't get it mixed up, because these are intervals. So the interval where it's increasing, as you can see, from -4 to -3, going up, here as well going up, and here as well you're going up. So let's start from left. You start from -4 to -3. What's another interval where it's going up? This looks like -1.5, right? So -1.5 up to 1, and then the last interval is from 2 to 4. Okay, and then it's decreasing on, again, these are the intervals. From where? Well, let's see. Decreasing from minus 3 to minus 1.5. So minus 3 to minus 1.5. And then where else? So where is it? Sliding down. And then here it's again sliding down. So from 1 to 2. And then letter B, we look at all the local max first. And then what are the local max? Local max is where you reach a top. Again, you reach a top, and you reach another top. So you have a mountain top, that's on the side is half, I guess half top if you think about it, because it occurs at an endpoint. So where is it? It's at -3, 1. These are points. Remember, these are not intervals, these are points. And then 1, 1, and the last one is at 4, and y is 2. Then let's look at the local min. Where are the local min? It occurs at -4, 0, right? Where else? -4, 0. Negative, that looks like a -1/2. So -1.5 minus 1, and then the last one is 2, 0, right? That's a local wherever you see a valley or a dip to 0. Okay, and then out of the local max, compare the largest value of the y's, and we see that this is your absolute. Okay, and then for the absolute minimum, compare the y values, and you see that this is your absolute minimum, because it's -1 is the least value on the whole graph. All right, finding open intervals. Remember we said that if you have a continuous function on a closed interval, you are guaranteed by the extreme value theorem, you're guaranteed to find a an absolute max and min. But if it's not continuous, as in this case, then you won't be guaranteed that you'll be able to find. Sometimes you will, but not all the time. Okay? In other words, we cannot invoke the extreme value theorem to say that, hey, we've got the absolute max or absolute min, because it's not a continuous function, as in this problem. But still, we can see from left to right where the curve is increasing, okay, and where it's decreasing. So for letter A, the function is increasing on the interval, on intervals, let's see, from -4 to -1. You see how we are rolling up, and then from 1/2 or 0.5, right? That's 0.5, 1/2 to 2, and also from 2 to 4, you see that you have a sloping upward again. Then decreasing on where? Oh, the only time that it's decreasing would be from -1 to 1/2. So on the interval from -1 to 1/2. Okay? And then letter B. We have to locate our local maxes. So let's take a local max. We see that there you reach a top here. That's a local max. That's another local max. So let's locate those points. You have at -1, 2, because the y value is 2. And then where else? When x is equal to 2, y is 1. And then when x is equal to 4, y is, when x is equal to 4, y is 3. Okay, and then local min at where? Well, we've got a local min right here, here, and I think that's about it. So you have a local min at -4, -1, and then at 1/2, -1. Okay, now based on these, remember we cannot just compare the y values, in this case y, because it's not a continuous function, so we can't guarantee. So we do have an absolute maximum. So the absolute maximum is when x is equal to 4, y is 3. But look here, you have two local minimums, but it's not an absolute because there are still y values below -1. You see these? These are the y values below -1. The problem is because you have open hole here, you have a hole here, that means the function is not defined at x equal to -2 here. But it's just getting closer and closer, so it's like a right-handed limit that approaches -2. So you don't have an absolute minimum. So you see, because we don't have a continuous function on a closed interval, there's no guarantee that we'll get an absolute extreme value. All right, so find the open intervals. Again, let's do that. Let's say, where is it increasing? And then where is it decreasing? Okay, so on the interval, right, so you start from left again. So you move and we see that the ball is rolling up, it's going up. It's just like you're riding a roller coaster and you start here. So you go up, go down, up, down, and up. So where we go up, that would be where you're increasing. So from -4 to -2.5. And then where else? From -1 to 1. And then where's the other interval? From 3 to 4. Okay, and then where is it decreasing? Well, it's from -2.5 up to -1. You see that from -2.5 to -1, the ball is rolling down. And then where else? Right here, this side. So from 1 to 3. So from 1 to 3. From 1 to 3, see that it's rolling down. All right. Now, let's decide. Are we going to find local max and local min? Yeah. Let's just check. Local max and then local min. So where is it at? You've got a hilltop, another, well, no, because you take a neighborhood around 1 and there's if that had been covered, that's a local max. Well, that's a local max. So you've got it from when at the point -2.51, right? Because when x is equal to -2.5, y is 1. Then what's the other one? Going up, so when x is 4, y is 2. Okay, then local min, these are not local min because what's going on is that these are asymptotic about this line, so this will continue downward. And then again, that will continue unbounded going down. So it will go down indefinitely. So the local min would be, if you take this open interval, then that's not a local min, that's not a local max. Here's a local min. So it's at 3, 1. Right, so where else? I think that's it. It's the only time where on an interval around there and here, nope. Here, nope. Here again, nope. So, and then is there an absolute max? No, because look, that goes up there, but the problem is it's not a covered point. So that point does not belong to the graph. And then since this is going down indefinitely, see how the curve is going to go down indefinitely, then there's no absolute min either. So all you've got are local max and mins, but no absolute max or mins. Now again, why did we not get the absolute extreme values? Because you have a function, although it's on a closed interval, the problem is it's not continuous, so you were not able to find the absolute extreme values.